Hi, this is be our final presentation on interference detection and classification in Open RAN using neural networks. In a typical wireless communication network such as the Open RAN, real-time interference detection is very important and in order to ensure optical network performance and the quality of service. So there are different various of interference that could occur in a network, which requires fast and accurate detection and control. So we plan to develop a neural network-based application that detects and classifies this interference and within 10 milliseconds to 1 second. And the challenge here will be to balance the classification accuracy and the inference speed under the 10 milliseconds to 1 second latency constraints. And so for our data set, we'll be using a real-world LTE or 4G ORAN testbed, which comprises of the base station, the mobile device, and the jammer component. That's why using to generate this interference. So the jammer will be used to generate the different kind of interference, and the base station and the base station is going to be used to generate this IQ data, which will be to generate data sets of the spectrogram for us to be able to classify the various form of interference. And this shows the high level overview of the whole closed loop control operation. So the base station and the mobile device, they are communicating, and the jammer is also communicating, trying to disrupt their signal. And so the base station will be generating these IQ samples, as I mentioned earlier, and it's going to forward this IQ data into the narrow time component, and which it will be converted to spectrogram, and the spectrogram will be fed into the ML classifier, then which will now like make inference and send the control back to the RAN. And for the inputs to the machine learning model will be spectrogram images of 128 by 128 by 3, which represent the channel states, and the classes are three when there's no interference, and when there's continuous wave interference, and when there's checked interference. And the output will be either of these three classes, and the XAP is going to send a control to the RAN in order to mitigate these different types of interferences. And so for our data set, we have the SOI, the CWI, and the CI. And for the um, exploratory data analysis on the spectrogram data set. We're talking more on the TSNE, which kind of show the distinct distinction between the three classes of data, with some variations on overlapping between the SOI and CWI. So we'll be putting this into consideration when we are developing the model, and we'll talk more about it in the results section.
Okay, so we split our data 70, 20, 10 for training. We had 6,000 images, 2,000 images per class, so that we don't have to do with any class imbalances. So the spectrogram images for the MLP, we have 256 by 256, and then for the efficient net, which is our final model, it expects the images to come in 224 by 224 by 3. So we did data augmentation, but also only for the efficient net. We flip horizontally and also adjust the brightness randomly. So for model training, the MLP, we use a loss of sparse categorical cross entropy and then a learning rate as mentioned. And then we train this for just 10 epochs with A100 GPU. So for efficient net, we freeze the lower layers and then only unfreeze the last upper 30 layers for training, and we train that with early stopping. So the metrics, we have accuracy, precision, require font score, and then the confusion matrix. More about it later. So for the MLP, we just have three hidden layers of 128 by 128 by 64 units, and the outputs, we have just three corresponding to our three classes. For the efficient net, we have efficient net B0, which is pre-trained on image nets, and we add our custom layers for the classification head, the global average pooling layer, and then we have dropout, and then the dense layer corresponding to those three classes. So for the MLP, we achieved like an average inference time of 2 milliseconds, which was really good. And then the test set evaluation, we saw an accuracy of like 98.31%. If you take a look at the confusion matrix, you see that everything was classified very well except the overlap between CW and SOI, which we saw initially in our data exploration. So for the final model, efficient net, we're able to improve the accuracy from the MLP baseline to 99.35, which is very good. But because the efficient net is much deeper in a bigger model, the average inference time increased to almost 9 milliseconds, and which is still fine. It is still below the 10 millisecond requirement for the near real-time rig. And that is performing excellently. But for a latency critical application, we would rather use the MLP giving us 98% accuracy and 2 milliseconds than use this. So if it is a normal application, then we will stick with this efficient net because it's giving us the best accuracy. And if you look at the confusion matrix, we're able to improve it quite well from the previous one. Yeah, we previously have experience developing a cellular testbed and XApp for Open RAN systems, and also experience with machine learning. These are references, and thank you.